Tarde a todos, bienvenidos a esta nueva conferencia precongreso. Faltan pocas ya, estamos en nada de nuestro congreso a finales de este mes. Solo como información, no olviden que las conferencias se graban y podrán consultarlas posteriormente en el sitio web del quinto Congreso de Amitos. Y me gustaría agradecer a Sina Moayemi, al doctor Sina Moayemi, quien está hoy con nosotros, quien será nuestro conferencista, un tema sumamente interesante, y qué mejor que el doctor Miguel Ángel Mánica, quien también nos acompañará como coordinador y maestro de ceremonias en esta conferencia. Bueno, Sina, thank you, really, to be with us today. Good luck, my friend. Thank you.
Thank you. Thank you so much.
Perfecto. Antes de darle la palabra al ponente, voy a leer una breve reseña. Por si hay alguien que nos acompañe también en el extranjero, la leeré rápidamente en español y posteriormente en inglés y ya le daré la palabra a nuestro conferencista. El doctor Sina es un especialista en geomecánica y líder de proyecto del software RS3. Él obtuvo su doctorado en geomecánica computacional de la Universidad de McMaster. Ha hecho investigación enfocada en la propagación de fracturas en suelos y concretos 2D y 3D, usando los elementos finitos extendidos. También ha visto temas de fracturamiento hidráulico, modelado termohidromecánico y análisis de propagación de daño en estructuras de concreto afectadas por reacciones químicas. Él comenzó a trabajar en Rocscience en 2016 y ha desempeñado un rol primordial en dirigir y contribuir investigación para el desarrollo de los software RS2, RS3 y EX3. Okay, so just a quick introduction in English. Dr. Sina is a geomechanics specialist and lead project manager of RS3 software. Obtained his PhD in computational mechanics from McMaster University. His research was focused on 2D and 3D crack propagation in soil and concrete using extended finite element, hydraulic fracturing, THM modeling, and analysis of damage propagation in concrete structures affected by chemical reactions. He joined Rocscience in 2016, and he has played a pivotal role in leading and contributing extensively to research and development work on RS2, RS3, and EX3. So, Sina, thank you very much. The floor is yours.
Thank you so much, Miguel, Juan, for the introduction. And I just wanted to say hello to everyone. Hello from Toronto. At the beginning, I wanted to thank the organizer for inviting me and Rocscience to your amazing Congress and giving us the opportunity to introduce one of our 3D products that is used a lot in tunneling and also mining. I really appreciate it. I hope you enjoy my presentation, and at the end we can have a great conversation together. Okay, without further ado, let's talk about tunneling. So the topic for today's presentation is streamlining 3D finite elements modeling for tunneling application. The agenda for today is shown here. First, I'm going to introduce briefly Rocscience and one of our programs called RS3. I introduced you the tunnel designer tool that we have in the program, and then we do a demo together to create a 3D model with the tunneling and sequential excavation. Then I show you a case study that that I created basically based on one of the papers and real cases in Turkey, and at the end we are going to do the final conclusion. So about the Rocscience, we are the world leader in developing innovative 2D and 3D softwares for civil, for mining, and for geotechnical engineering. From a team of 4, 25 years ago, basically Rocscience was established from University of Toronto. And now after 25 years, as you can see in the images, the company has grown a lot, and now we are a team of 80 people. We have 4 offices in the world, one in British Columbia in Canada, one in South America, in Africa, and also in Australia. And our representatives are all across the globe. And right now, the number of users of Rocscience products are more than 10,000 in the world. Here you can see a list of our products that we have. Currently, we have 19, and each of these programs are designed for a specific purpose to fulfill your needs in the geomechanics or civil application. For example, some are focusing on slope stability in 2D, 3D. Some are for just finite element analysis, which gives you a wider capacity to do different types of analysis. Some for settlement, for just underground excavation. So each of them are designed for different purposes. If you want to know more about them, I recommend you to go and check out our website and read more about each of these great products. One of the benefits of using our programs is that they can communicate with each other. For example, if you have a 3D model and you want to take a specific section into RS2 and do the 2D analysis on it, in your program, you can create it. You don't need to recreate your geometry. You don't need to go and redefine your material properties. So these are all the benefits that you can get if you use a combination of our products. But today's focus is on RS3. So RS3 is our 3D general finite element package with a wide range of application. I can categorize that into mining engineering and civil engineering. For mining, you can do a slope analysis. You can do modeling of large-scale mines, as you can see here, or you can do sequential underground excavation. We recently added a new functionality to the program called Discrete Fracture Network, which makes the modeling joints in 3D and creating them in 3D very simpler than before. It's going to make RS3 very unique in the market. I actually had a separate webinar just focusing on DFN about a week ago. It's already in our YouTube channel. If you are interested, you can go and check it out. And for civil engineering, you can do consolidation, seepage analysis, dynamic analysis. With the built-in tool that is called Tunnel Designer, you can create tunnels, you can assign the supports, and that's what we are going to focus on today. And also you can do deep and shallow excavation. The workflow in RS3 is shown here. The first step, you need to go and create your geometry. If your geometry is simple, you can just use the some of the primitive shapes that we already have in the program, and you can combine them together to create your geometry. But when it is more complicated, for example, you might have the geometry in, let's say, AutoCAD or in other softwares, and you want to do a 3D analysis on them, you can import it to RS3 and then create your geometry based on that. We have a very powerful repair tool, so it can look at the geometry. If, for example, there is a hole on the surface, or if there is a very edgy surface in the imported geometry, it can fix it for you, it can repair it for you. Also, if you have, for example, point cloud, you can import it to the model, to the geometry, to the program, and then it's going to create the surface based on the imported points for you. Next step is to defining the materials. In RS3, we have a comprehensive material library for soil and for rocks, like Moore-Coulomb, generalized Hook-Brown, anisotropic materials. In addition to that, we have a borehole manager that if you know the location of the boreholes and you know the layers, the thickness of each layer and the assigned material, you can define them in the program, and we are going to create the geometry for it. That's actually what we are going to use in the demo today. And then you need to do a 3D Boolean operation when you are bringing different objects, different volumes and surfaces to the model. We need to find the intersections between them. And that's what you are going to do in the divide all process. The first three parts is almost shared between all of our 3D packages. And they're almost similar. So we had a dedicated webinar only focusing on model creation that I did it with my other friend and colleague, Dr. Sina Javan Khoshdal, another Sina in the company. We did it about a month ago. It's also available in our YouTube channel. You can check that out. Depending on the type of analysis that you have, for example, if you have seepage analysis or dynamic analysis, you can have different types of boundary conditions. You can have, for example, assign the total head or pool pressure in one side of the geometry. You can have, for example, absorb boundary condition, nodal mass, or free field. If you have the dynamic analysis, you can also define the projected load. So you set the location of the load, and then it's going to project it to your geometry, which makes the modeling much easier. After you define the loading and boundary condition, you need to define the 3D mesh. So in RSC, we have the tetrahedral elements. It can be either 4-noded or 10-noded. The mesh generation is automatic in the program, but if you want to, let's say, create a denser mesh in a specific area, you can tell the program by defining the refinement region. And after you define the mesh, it's all ready to do the computation. In RS3, you can also do the SSR analysis, which is shear strength reduction method. So if you have a slope, you can find the factor of safety. You can do fully coupled or uncoupled for a solid fluid analysis, and also you can do dynamic simulation. When your analysis is done, you can go to the result tab and then see your results. You can see them on the external boundary. You can see the results on the excavation boundaries. You can, for example, have contour planes to see the results on a specific plane that you want to see them. Or you can define query lines. You can export it to the Excel and compare your results with, let's say, analytical solution. Also, it can have, if you have the sensor data or LiDAR data, or you have them as a CSV file, you can import them to the model, and you can compare your results with the measured data from the site. That's another functionality that we have in RS3. So it was a brief introduction of the program. But now let's talk about tunneling and how RS3 can help us for modeling the tunnels. We added a feature a few years ago in RS3 called Tunnel Designer. But before I explain it, I want to mention why we added this tool to the program. So imagine you have a simple tunnel. Let's say you have a cylindrical shaped tunnel and you want to do sequential excavation. Before we add this feature, you needed to divide the cylinder into smaller pieces, then define multiple stages, pick each of these small pieces, update the materials to tell the program, okay, this is going to be excavated in this region. And then later on, if you want to have, for example, bolts or liner around the tunnel, you need to pick the surface and do all of these steps manually, which can be extremely frustrating and time consuming. And that's why we designed this tool in the program, so it can make the tunnel design much faster and easier. When you open the Tunnel Designer tool, that's how it's going to look like. So it has 3 different panels. In the left panel, you can define any number of tunnels that you want to have in your model. And for each tunnel, there are different functions. For example, you can define the profile, the shape of the tunnel. You can define the path. You can define the sequence of the excavation. In the middle panel, depend on what you have selected. For example, here we pick the path. There are different parameters for defining the path. For example, you can extrude it, or you can define the specific shape for the extrusion of the tunnel. You can define them in the middle panel, and in the right panel, you can see the shape or the profile. of the tunnel, either in 2D or in 3D. The steps of using the tunnel designer tool is shown here. First, you need to create the profile of the tunnel. You can even draw it in the tool, or if you have the location of them, like in AutoCAD, you can import the coordinate and it's going to create it for you. Then you need to section your profile into a smaller region in case you need to. For example, if you want to excavate first the top part and then continue the bottom part of the profile, you need to define multiple sections here. And then you need to define the path to make it the 3D. Then you can define the sequence of excavation. For example, you can tell the program, okay, excavate for me every 2.5 meters, and keep repeating that at each stage. You can see that initial tunnel path that we had, now it's divided into smaller pieces with the length of 2.5 meters. And then you can go and define the different types of supports. In RS3, we have beams, bolts, and also liners. And then you can mention when these supports are going to be added to the program. So it's a general scheme of how you can use the program and the tool. But before it gets late, let's start the first demo to see how we can really go and create some tunnels in RS3. So this is what we are going to make in just few minutes by the help of the tool. So I'm gonna open RS3. Okay. And this is the raw file that I already created in advance. And the only information that we have are the boreholes. So I define it just to save some time, but I show you how to define the borehole information. So you need to go to the material, then you go to the borehole manager. Then you can define any number of boreholes that you might have in your site. Then you need to specify the location of the borehole. You need to define the orientation, and then you tell the program how many layers are in the borehole and what properties are assigned. So that's what I did already in the program. If you go to the location tab, you can see all the boreholes in the model, and any of them that is selected, it becomes like highlighted for you. If I move to the different one, it will be highlighted for you. So that's how you can define the boreholes. Okay, I have them now defined in the model. Next step is I want to create the geometry based on this borehole location. So I go to the geometry tab and I create external box. I want to tell the program where my geometry is basically exists. What geometry I want to model. So you go and create the external box, and you specify the corners of the box. So let me input the numbers. This is the one of the corners, and I'm gonna define the second corner. And you click OK. So now I have a box, external box, and I also have this borehole. To intersect the borehole information with the box, as I mentioned earlier, you need to do a process called divide all. So I do the divide all process to detect all the layers, and now you can see all of those layers based on the borehole information are now created for me. You can see them in different views. If you double click also in any of the views, you will maximize that. And so we don't need any other information for the boreholes. I select them and I hide them. And the only thing we see is the geometry. And here you can also change the transparency of the geometry. Okay, so geometry is made. The next step is to go and create the tunnels. You go to the tunnel and pick Tunnel Designer. Okay, so the window that I just showed you earlier will appear for us, and now we are going to input the information. First step, you can rename, you can name your tunnel. For example, I'm going to call it tunnel example. And then you select the profile. Here we are going to define the profile. If you select the tunnel, we have different predefined shapes. For example, a square cavern, or you have horseshoe. You can update the parameters for it to get what is in your mind in your design for the tunnel. Or if you have the information of the tunnel profile, you can click on data table and copy and paste the information of the coordinates around the tunnel, paste it here, and it's going to create it for you. Or if you don't have any of them like me, you just go and draw it. So I'm going to create the simplest tunnel, which is the circle. I click on it, it asks me to define the center. So 0 and 0. I hit enter, and then it asks me to define the radius. So I'm gonna set the radius to be 3.5. And there we go. The tunnel profile is created for me. And the origin of that, the reference point is 0, 0. This is an important location because later on when I want to assign the tunnel to the geometry, I'm going to say, okay, move this reference point to this specific location that I want. All right, so we defined the tunnel profile. Let's go and define the path. So you can either extrude it, or if you have the coordinates of the path, you can, again, import it as a CSV file and it draw it for you, or you can even draw it. So if, for example, click draw, here I'm just gonna draw some random line, and you can see the tunnel can be created for us. But for simplicity, I'm gonna change it to just extrude it. I set it as 70, and now you can see I have a tunnel with the profile and with the length of 70. Next step is excavation. You click on the excavation. Here we only had one region for the profile. I select it, and now I can ask the program to do sequential excavation for me. So I check that option on, and I want the program to do the excavation every 7 meters. I know 7 meters is a lot, but it's just the demo, so let's go with it. When you update the length of the sequence, you can see it is now divided into smaller pieces. Now I have 10 pieces that is created for me. And I'm telling the program every stage, starting from the moment that I'm assigning the tunnel to the model, do the excavation. So in a stage 0, which means when I'm adding the tunnel to the model, it's gonna, the first part, the first 7 meters is going to be excavated. In the second stage, the next part is going to be excavated, and so on. But in most models, you want to, the first stage to be only the field stress, and then you do the excavation. So I'm gonna change it to stage 1 and click apply. Okay, the sequential excavation is defined. Next step is to add support. So I add, click add support, and you can see the different options for it. You can have bolts on face or perimeter of the tunnel, the same thing for liner, or you can have beams. First, let's add the liner. So the program asks you, where is the location of this liner? So you need to define it. You click on the define, and then pick some points all around the tunnel. And then when you are done, you click, right click and hit done. And there you go. The liner is added for me. Next, you need to specify the liner property. If you click on this pencil icon, you can see that for liner, we have like a standard plate element. You can have geosynthetic, which works only on tension, or we can have reinforced concrete, that you define the ratio of reinforcement and concrete, and then you can do the analysis. Okay. So I define the location of the liners, and then I can say install the liner one stage after each excavation. In case you have some temporary lining in your design, you can also tell the program to remove it after a certain amount of stages. Now let's add bolts, but this time instead of adding the bolts all around it, I want to assign it only to a portion of the liner tunnel. Sorry. And you click done. You can change the length of the bolt. You can change the spacing of the bolt, for example, 1 meter, make it very dense. And if you view that in 3D, you can see the spacing along the path. So I'm going to reduce it to 2.5. And also, there is an offset option for us. So you can see that bolts are added right at the face of the tunnel. We don't want it. We want to add some offset for the bolts. And by default, all the bolts are added normal to the face, but you can always specify the orientation for them if you want to. And similar to liner, you can say when the bolts are going to be added and where they are going to be removed. All right, that's it. So that's how you can define the sequence of excavation for your tunneling. And then I click OK. Now let's add these these tunnels to the model. So you go to tunnel, add tunnel. You pick the tunnel you defined. We only had one. So we pick that one, and then you pick the location. Remember, I mentioned the reference point before was 0, 0. Now I'm going to ask the program to move this to, for example, 7 and -15, and add this at stage 1. And then you click OK. There you go. The tunnel is added. Let me hide these layers to see what we really created in the tunnel designer. If you go to the support tab, so as I mentioned, the first stage, we just want to have the field stress. We don't want to see any excavation, and we are not seeing any. Then next stage, we did the excavation. The stage after that, I expect two things. One is to see the bolts and lining around the first excavation, and also the second sequence should be excavated. And you can see it is all added for me. Very simple, just with few clicks. Let's go ahead and add another tunnel in a different location. Tunnel, add tunnel. And this time I want it to be -7 and -15. This time I want to add the tunnel, not in the first stage. I want to add it, for example, in stage 6. And then you click OK. You can also see the number of stages at the bottom. And whenever you add the tunnel, it's going to be extended. The number of stages will be extended. OK, so one more time, let me hide the layers. And this time when I'm moving in the stages, you can see two different sequences for the tunneling. Very simple. So we added the tunnel. Next step for modeling is to do the divide all. I want to find the intersections between these tunnels and the geometry we just made. So I click divide all. Now the divide process is finished. Next step is to make sure the loading, the initial loading is what we want to have. So if you go to the field stress tab, you have two different options. You can either have a constant field stress or a gravitational, and you can mention the ratio between the vertical and horizontal stresses. So here we have K0 condition, which means they are the same. I'm not going to change the default. Then we can apply the restraint. So what we need to do, we need to fix these two faces to be fixed in Y direction. So I'm going to change my selection mode to face selection. I'm going to select this face, hold the control key, select the other face, and I'm going to fix it in Y direction. I'm going to select these two and fix it in X and Y. And the bottom part is going to be fixing X, Y, and Z direction. That's it. Next, you need to create the mesh. So I'm gonna go create the mesh. You have two different options. You can either have uniform or graded. So uniform means you are going to have the same element size everywhere in your geometry. But if you use graded, the program is smart. Wherever you have the excavation, for example, around the tunnel, it's going to give you a denser mesh, and when you are far from the tunnel, it's going to give you a larger elements. And you can see that here. Around the tunnel is very dense, and far from it, it's going to be a larger element size. And that's it. So we created our model. You can go to the compute and hit compute, and you will see your results. I already computed. It's going to take around 3 to 4 minutes to run for all 18 or 17 stages. And then when it is done, you will be able to see results on the external boundary. You can see, for example, sigma 1, sigma 2. You can see, for example, displacement in your model. If you want to see the results only around the tunnel, so you need to go and hide the exterior contour, and you can activate the excavation contour. I already did that before. You can see the results only around the tunnel. Or if you want to have a contour plane, for example, I want to have a plane in XZ coordinate. You click add. Now you see the results of the total displacement in the specific location that we wanted. So we already see the results for solid. If you want to see the results for example, bolts or for liners, you need to change the data type. For example, if you switch to liners, you can see some information such as displacement. You can have axial forces or moments. But one of the important things that we need for tunneling, we don't want to see the lining results in the global coordinate. We want to see them in the local coordinate of the tunnel. About 2 years ago, we added this functionality also in RS3. Let me show you how you can define the lining coordinate. So I go back to the previous model. So this is actually the model that we were making together without the mesh. So what the thing you need to do is to pick all the surfaces around the tunnels that you want to have to define those local coordinates. I already defined those surfaces. You can see you just need to go and pick all of them, then go to support, liners, and define liner local coordinate for tunnels. And then the program asks you what is the direction of the tunnel. So it is extruded in Y direction. And then you click OK. Now you can see this tunnel frame is created for me. That X direction is along the tunnel, Y is in the direction of the path, and Z direction is normal to the tunnel. So when we want to see the results for liner in this local coordinate, you need to ask the program to show you the results instead of global in the tunnel frame that we just defined. And that's how you can get your results in the proper coordinate. In the next example, I'm going to show you actually the results that I captured for the liners using liner coordinate system. So let me go back to the presentation and show you one of the case studies that was done for a railway tunnel excavation in Turkey. So I actually found this paper that you can see here, which was written by 2 professors in Turkey. So what they were focusing on, it was modeling of a high-speed modeling of a tunnel for a high-speed train project with a length of 1.2 kilometers, not too long. But the tunnel was placed in a weak ground condition. The tunneling was started in 2013. However, at the beginning of the excavation, they saw a failure of the tunnel. So they needed to update their design. They revised that, and then they did the full project. So in this study, in this case study, a new tunnel support system is examined to see how much is the settlement, or are we going to see the failure or not. So this is the location of the site. It's as I mentioned, it's in Turkey. And here you can see the geological plan and also a cross section. So it's, as I mentioned, for the length of 1.2 kilometer. These black bold lines are basically the boreholes. So we are focusing on only this specific section. You can see there are 9 layers of materials that I defined it in the borehole manager. And we had sand layer, clay layer, and silt layer. I used the Moore-Coulomb criteria to define the properties of each. The first thing that I did, I tested the original design. So this is how the original tunneling design looked like. I applied that using Tunnel Designer to the model. And after 1 or 2 stages of excavation, I saw a huge failure. I got like 1.1 meter displacement, and the program even didn't converge, which is a good indication that your design is not safe. And also you can see the failed elements. It's I was happy that I could capture that also numerically. So what they did, they updated the design. The main change was they added forepoling, or they added grouting on top of the tunnel to make it stiffer, and then they did the excavation. So I did the same thing in RS3. Here you can see an animation that how the sequence of excavation was done. And you can see these steps here. So in the first step, I added the field stress, then I add the forepoling, then I excavate the top heading, I install the shotcrete there, I excavated the bench, I added shotcrete and bolts, and the same thing for the invert, the bottom part of the tunnel. And here are the results that I got. So the maximum vertical displacement that I got from the top section of the tunnel was around 4 centimeters, and also 2 centimeters for the horizontal displacement on each side of the tunnel. Also, here you can see the vertical and horizontal displacement, the propagation of it after each sequence of excavation. Here you can see which areas are yielded. As we all expected, most of the yielded elements are around the tunnels. And also at the top, we can see a little bit of failure in tension because they are not confined at all, and the tensile strength of the material was low. So we saw some failure on the top layer as well. Here you can see the results for liner. I got the results from the in the liner local coordinate, as I explained to you earlier. You can see the circumferential force, you can see normal displacement, and also moments around y-axis. Y is basically along the path of the tunnel. And I defined the query lines, so you can see the moments around each of the each liners, the liner on the top and also another liner on the bottom. These huge values are basically concentrated at the corners, and as you know, at the corners we always have the singularity, so that's why the moment is a little bit high. In addition to that, I did a dynamic analysis. I found one of the records, the earthquake records in Turkey, and I applied that the acceleration to the base of the model. And also I used the free field boundary condition on each side of the geometry. And I did the analysis, dynamic analysis, and I captured the horizontal and vertical displacement on the top and on the side of the tunnel. So the maximum change in the horizontal was measured about 2 centimeters and also 1 centimeter for the vertical displacement. That's all I wanted to mention today. So let's just do the quick conclusion here. As you saw in RS3, with the help of Tunnel Designer, you can do the full 3D analysis of a real project. You can do it very quickly using the tool. We saw the effect of supports, lining, bolts. We could do the sequential excavation. We could do the seismic analysis, all using the program. But my main point here is the last one. So whenever I'm going to the conferences or see the case studies, most of the time for tunneling, I'm just seeing they are doing the 2D analysis, which I think is not good. With the improvement in the softwares and in computers, the 3D analysis for tunneling is inevitable. Using the classical and experimental formulation to model the whole tunnel with just a 2D cross-section cannot see the real 3D effect of excavation, and the results are always debatable. However, as you saw here, using a powerful 3D program like RS3 can help you to do the full analysis and help for a proper design. Thanks again for the opportunity that you gave me to talk to you guys, show you the some of the cool features that we have in the program. I'm not sure how many of our audience have used RS3 or using RS3, but if you are using it and you have any feedback, you want to see any feature to make your design faster and better, let me know. If you want to try RS3, we provide you a 30-day free trial. So please send me or Raul or representative in South America, and we can provide you the link. Thank you so much.
Thank you, Sina, for this very nice presentation and for showing us this very powerful tool. Please, the audience, if you have any questions, you can put it in each of the chats, in whichever. We have a comment of one. I think you can read it. It is impressive how easy the tool makes it to analyze a construction sequence of a tunnel. This is very important for professional practice.
Thank you so much. Yeah, I totally agree. It's like without the tool, it's gonna be so hard for creating the tunnels. But with the tool you saw, with just few clicks, we could just create the actual model. Yeah.
So please don't hesitate to put your questions in the chat. Maybe in the meantime, I can make a question for myself. So when you were playing with the path tool,
yes,
you draw a very sharp angle in the line.
Yes,
but then
yes.
The tunnel that was created was very smooth. Is there some default parameters regarding the curvature radius when you are drawing? Or
so whenever you draw, basically the program always does some smoothing for you. But if you, for example, import the location of them, input it like in a CSV file, then it's just going to follow the path that you already inputted the program. Yeah.
So if in your file you have sharp turns, it will respect those
Yes.
shots.
Yeah.
Very
I can
good.
see one question. Jose is asking me, can the program simulate the degradation of concrete over time? If we don't have a built-in functionality for it, but in the program you can stage the properties, the strength of any of the materials. For example, you can mention, let's say, the F prime C is changing by time. You should input that to the program. You should say in stage 1, this is the value for F prime C. In stage 10, for example, this is the value. That's how you can emphasize the degradation, but we don't have any built-in function to does it for you automatically.
Perfect. There is also another question from Jose Luis Gonzalez. Can the
Yeah.
tunnel be modeled together with vertical ports?
Yeah, there is no limitation. You can do that. Yeah.
And what you were mentioning about the evolution of the materials, you have to do this by defining different materials, or
no,
you
there is
function
something called a stage factor. So you don't need to define multiple. You just say, for example, modular elasticity is changing with these factors. Yeah.
Perfect. And for instance, if in one stage you make one excavation, how this excavation is dealt during the stage? Is like a ramp loading, or is just you take this
Yeah,
volume?
you just remove the material. Yeah, you just remove it.
Okay. Let's see if we have one other question. Maybe in the meanwhile, one question also from myself. Can you go back to the slide where you show the plastic points in the simulation?
Yeah. Yeah.
So the green ones are the shear ones?
Excellent. Yeah, the green ones are shear. The purple ones are tensile failure.
It's kind of strange, these shear points in the bottom part of the model, right?
Yes, I agree. It could be because of a very large element size there. Maybe if I was reducing it, it could improve the results, but they are not a part of the equation for designing the tunnel anyway. Yeah.
Yeah, very good. And maybe just one last question from myself. I saw, there is another one from Pauline. The safety factor is calculated with the fee reduction criterion?
Yeah, so we are using the shear strength reduction. For example, if your material is more Coulomb, then when your analysis is finished, you can always do SSR at the end. What we are doing, we are updating the C and phi, rerun the model. We keep repeating it until we reach a moment that we cannot solve the equilibrium, when your model is not converging, and that's the point we are considering it like as a safety factor. You should always design it to be like strong enough, basically.
Very good. And how the strength reduction method is easy with, for instance, more column, but as you go to more complicated constitutive models, it's harder to define this. How you define the reduction of the strength, right?
Yes, we have a documentation on it. We don't have it for all the constitutive models, but for example, we have it for more Coulomb or for generalized Hooke-Brown. They are very complicated, but the equations are already in the inner documentation if you want to see. Very good.
I think there is no other questions. I don't know, Juan, if you want to add something to the talk or some additional question.
No, thank you for me, but really thanks, Stina. It was very impressive. As we said, it is impressive how easy the tool is, and that is very important for us for the practice, the professional practice. really.
Yeah, thank you so much for the great feedback, Juan.
There is a last question that appear. Is it possible to vary the constitutive model along the length of the tunnel to adequately represent the behavior of the soil of rock?
In this case, you need to update the materials. Otherwise, for one, like you cannot specify, for example, update the parameters based on the location. We have actually one functionality called discrete function that you can mention C, like the variation of C and phi based on the location, but it is not a function of your excavation. It is a function of location. So what I think Jose means is when you are excavating, then the material be updated along the path. If this is his questions, we cannot do it. You have to update the material manually. But if you are saying, can I see the variation of C and phi in the whole model using, like, for example, a function? Yes, you can do that.
Okay, thank you very much. So Juan, I think there is no any other questions. So I also, Jose Luis also congratulates you for the
Thank you so
very,
much.
very nice presentation. And I also agree with Jose Luis. So thank you for this very presentation. So I don't know, Juan, if you want to close the session.
Yes, just in Spanish. Vamos a tener a Rocscience en nuestro Congreso. Entonces, será una gran oportunidad para que quienes quieran acercarse y conocer más de estas herramientas que uno muestra de forma muy breve, Sina, lo hagan. O sea, es una buena oportunidad para conocer lo que en el mercado internacional se tiene. I said, Sina, we will have Rocscience in our conference. That would be a great opportunity to ask more about your tools, your software, your programs.
For sure, it's a great honor for us to participate. Thank you so much, Juan.
And maybe next time in Mexico, Sina.
Hopefully, I love Mexico.
Thank you. Thank you again. It was a very impressive conference. Thank you, Sina. Congratulations.
Thank you so much. Have a great evening, everyone.
See you guys.
Bye bye.
Nos vemos. Hasta la próxima. Gracias, Miguel. Gracias, Marcos.
A ti, Juan, Marco, Sina. Muchísimas gracias.
Thank you.
See you. Thank you.